Okay, so the birthday problem is a very well-known problem in probability. And it actually has to do with what's the probability of a coincidence happening. And just to give you a little bit of a high level, what it shows is that coincidences are more likely than you think. And maybe we'll talk a little bit as to why they're more likely than you think. Okay. So here's the problem. Suppose we have little n people in a room. Sometimes it's called the birthday paradox, but it's not a paradox. What is the chance that no two people have the same birthday? So how does this generalize? So before in the geometric distribution, what were we doing? We were picking out of an urn without replacement. But now we're thinking, okay, to generalize this birthday problem, we think of having an urn with capital N balls labeled 1 up through N. Little n balls are drawn uniformly with replacement. What is the probability that all labels are different? So let's start by working on the general problem. We specify a model, then we can apply it in the specific case of the birthday problem. Why is this a generalization? An urn with capital N balls are labeled 1 up through capital N, and we're going to draw little n balls with replacement. So in the birthday problem, what's capital N? It's 365, or you can say 366, because there are people who are going to have a birthday, which is the leap year. So 366 balls, each labeled 1 up through 366. And little n is how many people are in the room. Each person we think of as having a birthday that is uniformly drawn on days throughout the year. That's the assumption. Whether it's a good assumption, it's not really relevant to this. We're being given the model, we're assuming the model, and we're going to try to understand the consequences of that model. But that's why this is a generalization, right? We can generalize to arbitrary numbers of balls and so on. The point is that we're drawing with replacement, meaning, okay, I'm going to assign a birthday to person number 1. I'm going to pick from the days of the year. I give them a birthday. I go to person number 2. That person can have the same birthday as person number 1. So I have to put whatever ball I picked for the first person, I put it back and I draw again. Okay. So what's the probability model for this situation? Well, possible outcomes. So what are the possible outcomes? Omega, sample space. We're picking little n balls Each one is a number between 1 and capital N. There's no restriction. No restriction on them on the on them not being equal, like there were in the case of drawing without replacement. This can be expressed as square bracket capital N. Remember, that's our notation for the set of the first capital N integers raised to the power N. So that just means the first entry is anything between 1 and N, capital N. Second entry, anything between up through the nth entry, anything between 1 and capital N. How big is this? Well, it's the multiplication rule, right? How many possibilities are there for the first ball? And capital N. How many for the second ball? Capital N. How many for the third ball? Capital N. None of them interfere with any of the other, so it's capital N to the little n. We're going to assume probability is uniform on omega. We define the event of interest as outcomes such that the KIs are all distinct. What is the probability of Dn? Okay. What is the probability of Dn? So what we need to do is we say, well, there's little n balls, and we are going to pick in some order, okay? So we are assuming there's an order. So what I need to do is I need to pick little n balls in order from capital N balls. That's a little n permutation of capital N. Because I'm not allowing for there to be, I'm not allowing for there to be duplicates. So I can assign the first person any of the capital N birthdays, but then the second person has to be one of the remaining n minus 1 birthdays, and so on. So it's n fall n divided by n to the capital N, which we can write differently as, okay, the first person can have any one of capital N birthdays. Okay. And then the next person, what's the probability the next person has a different birthday than the first? Well, there's 1 over n possibilities that are no good, and the remaining are good. So 1 minus 1 over n, 1 minus 2 over n for the third person, and so on, all the way up to 1 minus little n minus 1 over capital N. So anyway, this is the calculation, and we want to see if we can get some intuition for this. Can we approximate? Can we get a nice expression for the value of the probability of D sub n? And the answer is yes, as long as n over capital N is small. So as long as, so think about it this way. What does it mean for little n over capital N to be small? That means that the number of people that need to be satisfied in this population, or the number of draws that we're making, is very small relative to the number of all balls of all balls. Okay. How do we do this? So let's use a Taylor expansion. log of 1 minus x is, Taylor expression is minus x squared over 2 minus x cubed over 3, etc., provided x is less than 1 in absolute value. And if x is close to 1, or if x is small, close to 0, this is approximately minus x. Why? Because these higher order terms disappear. Okay. Then what's the log of Pn? Okay, Pn is our probability up here. We write this as Pn. Sum from, okay, let me be a little clear here. Log of Pn, start by, it's the log of this product from I equals 1 to n minus 1 of 1 minus I over n. Log of a product is the sum of the logs. That's why we take logs. They're nice to work with. The sum of the logs. Okay. Log of 1 minus I over n, if n over little n is small, then I over if little n over capital N is small, then I over capital N is small for all I, because all of the i's are less than n, or even smaller. So this means that we can approximate this here by each of these terms by minus I over n. Okay. So we have a sum, and now what we can do is we pull the minus 1 over n out, minus n inverse, and we're left with 1 plus 2 up to n minus 1, little n minus 1. And this now is the sum of the first n minus 1 integers, right? So the sum of the first n minus 1 integers is n times n minus 1 divided by 2. And we have a negative 1 over n carried over. And so we're going to define this as now, this quantity as mu sub n. So what we can say is P sub n is approximately, so the log of Pn is approximately mu n. Now we take the exponent to get Pn is approximately e to the power mu n, mu sub n, for n satisfying this definition. Anyway, that is how we approximate this. How can we interpret this quantity? What's our intuition here? Okay. Well, let's think of it this way. What is the probability that let's just, instead of thinking about all of the little n draws, let's break it down to just 2 draws. Just any 2 draws. So what is the probability that draws I and j I less than j give the same ball? Okay, so this is pretty easy. How? So what's the probability that two draws give the same ball? Well, okay. Let's think about it. There are little n spots, right? And we're worried about, let's say, I and j, right? This is little n. Okay. Okay. So now, how many choices are there for the ith ball? There are n, right? We have to pick one of the capital N balls for the ith. So capital N choose one. We put that ball here. And then whatever ball that is has to go here as well in J. And once we pick the ball, there's only one way to pick to fill in the J spot. And then of the remaining n minus 2 spots, they can be arbitrary because we don't care about them. So there's n to the power n minus 2. And how many possible orderings are there? Well, that's the size of the sample space, n to the power n. And so this just simplifies to 1 over capital N. So the probability that any given pair are equal is 1 over n. Okay. Okay, then the next question is how many pairs are there? So we're assuming I is less than j. How many pairs are there? There's n choose 2, little n choose 2, which is n times n minus 1 divided by 2. So how many times would you expect two draws to be the same? So how many of the pairs I less than j would we expect to be equal? Well, each one has a 1 over capital N chance of being equal, and there's n times n minus 1 over 2 of them. We expect n times n1 minus n times n minus 1 over 2 times 1 over n. Okay. Which is minus mu sub n. So mu sub n is related to how many balls we expect to be how many balls how many pairs of balls we expect to be equal. Okay. So that's an example. That's a generalization of the birthday problem. And now we're going to talk next about inclusion exclusion, the generalized inclusion exclusion formula.